Welcome to lecture 6 on trigonometric functions. In the last lecture, we had introduced trigonometric equations and we discussed principal solutions and general solutions for some type of equations. For example, equations where of the form where sin x is equal to sin y. In this lecture also, we will discuss general solutions to similar type of equations like cos x equal to cos y and tan x equal to tan y. If cos x equal to cos y, so we are trying to solve trigonometric equations of the form, let us say if we are given that cos x equals half and we are interested in finding all the solutions to cos x equal to half. So, we realize that cos x is equal to, now half is equal to cos of 60 degrees, which is pi by 3. So, we have y equal to pi by 3 here, and then we want to find the general solution to this equation. So, towards that we will discuss some results and see how to find the general solution. So, we will first show that if cos x is equal to cos y, then it must be true that x is either equal to 2n pi plus y or x is equal to 2n pi minus y for some integer n. Similarly, we will also show that for all integer n, you take any integer n, then cos of 2n pi plus y is equal to cos of 2n pi minus y, which is also equal to cos of y. So, these two are going to help us to find the general solution to equations of the type cos x equal to something. So, we will start with showing that. So, we have to show that cos of 2n pi plus y is equal to cos of 2n pi minus y is equal to cos y for any integer n. So, of course, here the pattern is cos of a plus b, where a is 2n pi and b is y. So, this is from our previous lectures, we know that this is equal to cos a cos b minus sin a sin b. So, using that what we get is cos of 2n pi plus y is cos of 2n pi, a equal to 2n pi and b equal to y. So, cos y minus sin of 2n pi times sin of y. But we know that sin of any integer times pi, so sin of integer multiple of pi is 0. So, this term goes to 0. So, what remains is only the first term, and we also know that cos of integer multiple of 2 pi is equal to 1. So, for any integer n, cos of 2n pi is always equal to 1. So, therefore, this clearly is equal to cos of y. And similarly, cos of 2n pi minus y equals, so here we will use the formula cos a minus b is cos a cos b plus sin a sin b. So, this becomes equal to cos 2n pi into cos y plus sin 2n pi into sin y. Again, this term is 0, what we saw before, and cos 2n pi is 1 for any integer n. So, therefore, this is also equal to cos of y. So, we have shown that cos 2n pi plus y is equal to cos 2n pi minus y is equal to cos of y for any integer. We now show the reverse, that suppose if we are given that cos x and cos y are equal, then we will try to see the relation between x and. So, from this we get that cos x minus cos y is 0. Now, this is of the pattern cos a minus cos b, and which we from our previous lectures should be able to find it out. So, the formula that will be using here is cos of A minus cos of B is equal to, we get cos A minus cos B equals 2 into sine of B minus A over 2 into sine of B plus A over 2. So, we will use this formula here with A equal to x and B equal to y. So, what we get is cos x minus cos y equal to 0 is the same as writing that 2 times sine of y minus x over 2 into sine of y plus x over 2 is equal to 0. But this implies that either sine of y minus x over 2 is 0 or sine of y plus x over 2 is 0. We take that further. So, we start with the first condition that we derive now. So, sine of y minus x over 2 equal to 0 implies that sine of x minus y over 2 is also 0, because sine of minus x is the same as minus sine x. And we know this result that sine theta equal to 0 implies that theta is of the form n times pi, where n is some integer. So, therefore, this statement implies that x minus y over 2 must be equal to n times pi for some integer n. And then by simplifying this, what we get is that x is equal to 2 n pi plus y for some integer n. So, this was the first condition, and then the second condition was that sine of x plus y over 2 is equal to 0. So, let us examine that also. So, sine of x plus y over 2 equal to 0 implies that x plus y over 2 is equal to an integer multiple of pi for some integer n, and from here we get that x is equal to 2 n pi minus y for some integer n. So, essentially we have shown that if cos x is equal to cos y, then that must imply that either of these two conditions hold. Now, for this first condition to hold, this implies that x should be of the form 2 n pi plus y for some integer n, and this condition says that x should be of the form 2 n pi minus y for some integer n. And therefore, we see that cos x equal to cos y is only true if x is either 2 n pi plus y for some integer n, or it is 2 n pi minus y for some integer n. So, either of these two cases. So, here is a little example with cos x equal to minus half, and we know that cos of 2 pi by 3 is minus half. Cos x equal to cos y, which we just saw now, where y is equal to 2 pi by 3, and therefore, the general solution is x equal to 2 n pi plus and minus both 2 pi by 3. So, because if you remember, we had said that for any integer n, we had proved that cos of 2n pi plus y is equal to cos of 2n pi minus y is equal to cos y. So, using that we can say that all values of x of this form such where n is integer. So, this becomes the general solution to the equation cos x equal to minus half. For example, if we put n equal to 0, then we get 0 times pi plus minus 2 pi by 3. So, we get two solutions here, 2 pi by 3 and minus 2 pi by 3. With n equal to 1, we again get two solutions, 2 pi plus 2 pi by 3 and 2 pi minus 2 pi by 3. With minus 1, we get the solution minus 2 pi plus 2 pi by 3 and minus 2 pi minus 2 pi by 3. And we can keep on going like this, and all of these are solutions to this equation cos x equal to minus half. So, just like sin x equal to sin y and cos x equal to cos y, we will also try to get the general solution to any trigonometric equation of the form tan x equal to tan y. Of course, here both x and y should not be odd multiples of pi by 2, because tan of an odd multiple of pi by 2 is not finite. So, we will show that if tan x equal to tan y, then it must be true that x is equal to an integer multiple of pi, some integer multiple of pi plus y. On the other hand, for any integer n, we can show that tan of n pi plus y is the same as tan y. And this is not very difficult to see, because in the previous lecture we saw that tan of y is a periodic function, tan of x is the same as tan of pi plus x is the same as tan of 2 pi plus x and so forth. Nevertheless, we will still prove it here. So, tan of n pi plus y is equal to, so this is of the form tan of a plus b, and we know the formula for tan a plus b, it is tan a plus tan b by 1 minus tan a tan b. So, using that, here we get tan of n pi plus y equals tan of n pi plus tan of y upon 1 minus tan of n pi times tan of y. Here n could be any integer. So, n is any integer, but for any integer n, so for any integer n, we know that tan of n pi is equal to 0, because tan of n pi is sin of n pi over cos of n pi, and sin of n pi is 0 for all integer n. Therefore, tan n pi is 0 for all integer n, and therefore, this goes to 0 and this also goes to 0. So, what remains is that this becomes equal to tan of y, which proves that tan of n pi plus y equals tan of y for all integer n. And then we will also show that the reverse statement, which is that if tan x and tan y are equal, then it must hold true that x is equal to n pi plus y for some integer n. So, let us say we have tan x equal to tan y, and x and y are not odd multiples of pi by 2. So, we get from here we get this, and then since tan x is sin x by cos x, we get sin x by cos x minus sin y by cos y equals 0, from where we get sin x cos y minus cos x sin y over cos x cos y equal to 0. But since x and y are not odd multiples of pi by 2, cos x is not 0 and cos of y is also not 0, and therefore, this statement here is equivalent to sin x cos y minus cos x sin y equals 0. But this pattern we have already seen. This is of the form sin a cos b minus cos a sin b, which is equal to sin of a minus b. Therefore, this is the same as sin of x minus y and we know that sin of x minus sin of theta equal to 0 implies that theta must be some multiple of some integer multiple of pi. Therefore, from here we can conclude that x minus y must be some integer multiple of pi, and that implies that x has to be equal to n pi plus y for some integer n. Now, in the remaining lecture we will try to solve some find the general solution to some trigonometric equations which you might encounter. So, here this is a very general type of a very commonly seen trigonometric equation that you will come across. So, a, b and c are real numbers and we are asked to find the general solution to this equation a cos theta plus b sin theta is c. So, the way to proceed with this is that we divide both the left and the right hand side by square root of a square plus b square, and what we get is this second equation here. Now, if you see a upon square root of a square plus b square and b upon square root of a square plus b square, let us say that what we realize is that the square of this term plus the square of this term is equal to 1. And we draw a unit circle here with center at O, and let us say that this is the point whose x coordinate is a by square root of a square plus b square and whose y coordinate is b upon square root of a square plus b square. And of course, this point lies on the unit circle, and the angle of rotation for this ray OP is 5 degrees in the anti-clockwise direction. So, we have this phi here. So, let us now focus on this right angle triangle here, which I am drawing now. Now, in this right angle triangle, from the definition of cosine and sine, what we have is that cos phi will be equal to the x component of this point, which is a upon square root of a square plus b square, and sin phi will be the y coordinate of this point, which is b upon square root of a square plus b square. Now, using this fact here back into the trigonometric equation, what we get is cos phi. So, now find phi, this angle phi is completely known to us. Cos phi into cos theta plus sin phi into sin theta is equal to c upon square root of a square plus b square. But if we see this expression on the left hand side here, it is of the form cos a cos b plus sin a sin b, and therefore, it is equal to cos of theta minus phi equals c upon square root of a square plus b square. And therefore, this is the trigonometric equation for which we are asked to find the solutions to theta. Now, what we see here is that on the left hand side we have cosine of theta minus phi, and we know that the range of the cosine function is between minus 1 and plus 1, and if that has to be equal to this right hand side, it must hold true that mod of c over square root of a square plus b square must be less than equal to 1. So, a solution will exist to this trigonometric equation if and only if this condition is satisfied. So, only if this condition is satisfied are we going to have a solution to this trigonometric equation, otherwise there is no solution to this trigonometric equation. Now, let us assume that this condition is satisfied. So, in that case what we just need to do is we will say that we again go back to, so if this condition is satisfied, then we essentially go back and write this c over, because if it is less than equal to root, if this is less than equal to 1, then this must be equal to cos of some angle y. And then we will use what we just studied in some one of the previous slides, where we had said that for any integer n, cos of 2n pi plus y is equal to cos of 2n pi minus y is the same as cos y. So, we have a similar equation here, like cos x equals cos y. So, we have to treat this whole thing as x, and therefore, the general solution is that x, which is theta minus phi, is equal to 2n pi plus minus y for all integer n belonging to, so for all n belonging to z, the set of, so z is the set of integers, and therefore, the final general solution for theta is equal to phi plus 2n pi plus minus y, where n is an integer. So, this is what is the general solution to this trigonometric equation, but this general solution will exist if and only if this condition is valid or it holds. Now, let us discuss another problem. So, here we are asked to find, so now if you see we have two variables now, whereas what we have been studying so far was to solve equations, trigonometric equations where we have only one variable. So, initially it might seem very tough, but then what we can do is we can do some substitution and then get the solution. So, we have to find the solution set of this system of equations. So, what we see now is that from the first equation here, we can write that y is equal to 2 pi by 3 minus x, and we substitute this value of y in the second equation. So, the second equation now is cos of x plus cos of 2 pi by 3 minus x equals 3 over 2. So, finally, with the help of this substitution, we finally get a trigonometric equation in one variable x, and we should be able to solve that. Moving further ahead, we have cos x plus, we had cos of 2 pi by 3 minus x. So, we use the cos a minus b formula and we write cos 2 pi by 3 cos x plus sin 2 pi by 3 sin x equals 3 by 2. but cos of 2 pi by 3 is equal to minus half. So, we have cos x minus half cos x, and sin 2 pi by 3 is sine of 120 degrees. So, that is equal to square root of 3 over 2 times sin x equals 3 over 2, and then further simplifications, some simplification gives us half cos x plus root 3 sin x is equal to 3 by 2, or, and we know that half is cos of pi by cos of 60 degrees, which is pi by 3, and this is sine of pi by 3. So, we will get the form cos a cos x plus sin a sin x. So, we write the left hand side as cos of pi by 3 into cos x plus root 3, instead of this we write sin pi by 3 into sin x equal to, so this is our trigonometric equation so far. But this is of the form cos a cos b plus sin a sin b, which is cos of a minus b. So, we finally have cos of x minus pi by 3 equals 3 over 2. But we know that the cosine function is limited to the range minus 1 to plus 1, and therefore, cosine of any angle can never be equal to 3 by 2, and therefore, there is no solution to this set of equations. So, the final answer is that there is no solution. Let us see another question here. So, we are asked to find the general solution to this trigonometric equation, and if we see, this is actually, the left hand side is actually quadratic in sin theta. So, if we take z equal to sin theta, then we get the quadratic equation 2 z square minus 3 z minus 2 equal to 0. Equation here will be given by z equal to 3 plus minus square root of 9 plus 4 into 2 into 2, which is 16, over 2 times 2, which is 4. So, the two roots are 3 plus minus 5 by 4, but we see that if we take the root 3 plus 5 over 4, 3 plus 5 over 4 is 2, but z is equal to sine of some angle, and therefore, it cannot be 2. So, the solution z equal to 2 is not a feasible solution. So, the only other solution which remains is z is equal to 3 minus 5 over 4, which is equal to minus half. So, essentially the solution to this trigonometric equation is the solution to sin theta equal to minus half. So, we have sin theta equal to minus half. So, we know this identity that sine of pi plus x is equal to sin a cos b will be 0 plus cos a sin b. So, it will be minus of sin x. So, this identity is known to us, and if we substitute x equal to pi by 6 here, what we get is sine of 7 pi by 6 equals minus of sine of pi by 6, and sine of pi by 6 is equal to half. So, this is minus half. So, therefore, we can write that sin theta is sine of 7 pi by 6. So, we essentially have to find out the general solution to sin theta equal to sine pi 7 pi by 6, and this we have already studied in the previous lecture. If you recollect, we had said that the general solution to sin x equal to sin y is that x is equal to n pi plus minus 1 to the power of n times y for all where n is some integers, for all integers n. So, this is the solution. Now, the only thing is that here x is theta and y is 7 pi by 6. Therefore, the final answer is that the general solution to this equation is theta equal to n pi plus minus 1 to the power of n times y is 7 pi by 6 for all integers n. So, here we have another problem where we would like to find out the general solution to this trigonometric equation here. So, we write this as tan square theta plus secant of 2 theta is, because secant of x is 1 over cosine of x. So, this is 1 over cos 2 theta, but we know that cos 2 theta is cos square theta minus sin square theta. Also, we know that the numerator 1 here can be replaced with cos square theta plus sin square theta. So, the reason why I am doing this type of substitution is because I would like this whole left hand side to be in terms of tan theta, so that I get some kind of a quadratic equation or something like that, which I can solve and then get the general solution. So, what we have further is cos square theta plus sin square theta is 1, therefore, the numerator is replaced by this, divided by cos square theta minus sin square theta equal to 1. And then if we divide both the numerator and denominator with cos square theta, what we end up getting is 1 plus tan square theta over 1 minus tan square theta equals 1. So, the reason why we had to substitute this 1 with cos square theta plus sin square theta was that I wanted this whole of left hand side to be in terms of tan theta. And then what we eventually get is tan square theta times 1 minus tan square theta plus 1 plus tan square theta equals 1 minus tan square theta. So, essentially in this equation you multiply both the left hand side and the right hand side by 1 minus tan square theta, and this is what you end up getting. So, if we open up this braces, what we get is on the left hand side we get 2 tan square theta plus 1 minus tan 4 theta equals 1 minus tan square theta. And then if we rearrange this a little bit, what we get is tan 4 theta minus 3 tan square theta equals 0, and therefore, what we have is tan square theta into tan square theta minus 3 equals 0. So, for this to happen, either we should have tan of theta equal to 0, which implies that theta. So, this is tan theta equal to 0 can be written as tan theta is equal to tangent of 0, and therefore, that implies that theta is of the form n pi for all integer n. So, this is from this equation. So, either this should happen or we should have tan square theta minus 3 to be 0, which implies that tan theta is either plus root 3 or tan theta is minus root 3. Now, tan theta equal to root 3, but root 3 is equal to tan of 60 degrees, which is pi by 3, and then we have the same form which we tan x equal to tan y. If you remember a few slides back, we were just discussing that, and what we had said was that the general solution to this type of equation is that x is equal to n pi plus y for all n belonging to integers. So, using this result which we had proved earlier, we get with x equal to theta, we get that theta is equal to n pi plus pi by 3, and then similarly for tan theta equal to minus root 3, it can be written as tan of minus pi by 3, and for this the solution set will be theta equal to n pi minus pi by 3 So, the final solution to the trigonometric equation. So, from here we had come to the, we had substituted, and then what we got was that tan square theta into, so this implied that this holds true, and then we saw that this is true when either tan theta is 0 or tan theta is root 3 or tan theta is minus root 3. So, for this the general solution was this set. For tan theta equal to root 3, the general solution was n pi plus pi by 3, and for tan theta equal to minus root 3, it was pi minus pi by 3. But since we have an OR here, we have to take the union of all these three sets. So, this is the final general solution to this trigonometric equation. It is the union of all these three sets. We have another problem here, but here it is said that we would like to find the values of x only in the interval minus pi to plus pi, which satisfy this equation. So, we have 2 to the power of a series here. So, for example, the next in the series would be mod of cos cube x. So, in general, for any integer m, it is true that mod of cos m x is the same as mod of cos x raised to the power of m. And therefore, using this identity, we will try to simplify the exponent on the left hand side. So, therefore, what we get is equal to 1 plus mod of cos x plus mod of cos x whole square plus mod of cos x cube and so on. But what we realize is that this is essentially a geometric progression of the form 1 plus c plus c square plus c cube and so forth. And we know that this infinitely long geometric progression will converge to the value 1 over 1 minus c if and only if and only if modulus of c is strictly less than 1. So, let us use this result. Here of course, c is equal to modulus of cos x. By comparison, we are told that x should belong to the open interval minus pi to plus pi. So, in this open interval, there is only one place where c could be 1, which is when x equal to 0. So, so with x equal to 0, this sequence will not converge anyways, and therefore, x equal to 0 can anyways not be a solution to this equation. But for x not equal to 0 and x belonging to minus pi to plus pi, the sequence will converge to the value 1 upon 1 minus modulus of cosine of x. And therefore, we finally have the trigonometric equation as 2 to the power of 1 upon 1 minus modulus of cos of x is equal to 4, which implies that 1 minus modulus of cos of x should be equal to half, that is modulus of cos of x should be equal to half. So, now we have two cases here, either cos x is equal to half or cos x is equal to minus half. And the general solution to this equation will be the union of the general solution set for this equation and the general solution set for this equation. So, for cos x equal to half, the general solution will be the set 2n pi, because half can be written as cos of 60 degrees, which is pi by 3. So, we have cos x equal to cos y. So, cos x equal to cos y with y equal to pi by 3. So, using the formulation earlier, we had shown that the general solution for cos x equal to cos y is 2n pi plus minus y. So, we will have 2n pi plus minus pi over 3 n being integer. So, this is the general solution set for the first condition, cos x equal to half, union with the solution set for the other condition, cos x equal to minus half. We know that cos of 2 pi by 3 is minus half, and therefore, we have this equation is the same as cos x equal to cos 2 pi by 3. So, the general solution set for this second equation will be 2n pi plus minus 2 pi by 3 for integer n. So, the final answer is that the general solution to this trigonometric equation is the union of these two sets. But if we remember, what was asked in the question was not the general solution, but we were said that we should find all solutions for x between minus pi to plus pi. So, therefore, we have to only see which solutions here fall in the range minus pi to plus pi. And that is very easy to see. So, I will rewrite the solutions here. So, this was the final. So, this was the general solution set, and out of this we have to find out the solution lying in the open interval minus pi to plus pi. So, here for example, if we take n equal to 0 here in the first one, we get two solutions minus pi by 3 and plus pi by 3, and both of them are in the interval minus pi to plus pi. If we take n equal to 1, then we are outside that interval minus pi to plus pi. Similarly, if we take n equal to minus 1, again we are outside the interval minus pi to plus pi. So, from here there are only two solutions which lie in the interval minus pi to plus pi, and then we look at the second general solution set here. So, this is pi. So, here for n equal to 0 we get 2 pi by 3 and minus 2 pi by 3, and both of these are in the interval, they lie in the interval minus pi to plus pi. For n equal to 1 we get 2 pi plus 2 pi by 3, but that of course is going to lie outside the interval minus pi to plus pi. The other solution is 2 pi minus 2 pi by 3, which is actually equal to 4 pi by 3, and this also is outside the interval minus pi to plus pi, and therefore, will not write it here. So, and similarly for n equal to 2 and further also, the solution here will not be lying in the interval minus pi to plus pi, and the same thing will hold for n equal to minus 1. Therefore, the final answer is that the solutions to the trigonometric equation, so this trigonometric equation which lie in the interval minus pi to plus pi are these four values: minus pi by 3, pi by 3, 2 pi by 3 and minus 2 pi by 3. There is a very interesting problem. So, it says that let m be an odd integer, then if this relation holds true for all odd integers. So, m could be 1, 3, 5, 7, 9 likewise. So, it says that if this relation holds for all odd integers for every x, then we need to find the value of b0 and b1 such that this equation is satisfied for all odd integers m and for all x. But this might appear very difficult, but what we can do here is that if we put x equal to 0 in this equation, let us expand that first. So, what we get is sine of mx is, so the first term in the summation here is b0. So, it is b0, sine x to the power of 0 is 1, the next term is b1 sine x, then b2 sine square x, and all the way till bm sine x to the power of m. Now, if we substitute x equal to 0, the left hand side is 0, on the right hand side each of these terms will go to 0. So, what remains on the right hand side is b0, and therefore, it must hold that b0 is equal to 0. So, we have got the value of b0. Now, we need to find the value of b1 such that this is always satisfied for all odd m and all x. Now, let us consider the ratio of sine of mx over sine of x, and that will be equal to, since, so we are going to use this expansion for the right hand side, b0 is 0, so this is not there. So, we divide all of this by sine of x. So, we will get b1 plus b2 sine x plus b3 sine square x all the way till bm sine m minus 1 x, and then we take the limit x goes to 0 on both the left hand side and on the right hand side. So, when we take the limit, so we take this limit on both the, so limit x goes to 0 on both the left hand side and the right hand side. We know that the limit of the left hand side is equal to m, and on the right hand side if we see all these terms sin x, sin square x and sin x to the power of m minus 1, in the limit that x goes to 0, they go to 0. So, what remains is only b1, and therefore, the value of b1 is m and b0 is 0. So, now we take up another problem. So, we have to find all the solutions to this trigonometric equation here. So, what we see here is that we have sin x everywhere except in the first term we have a cos square x. So, if we replace this with in terms of sin x, then we are going to get a polynomial in sin x. Since cos square x is 1 minus sin square x, we get which is equivalent to writing that, because we have sin x here and sin x here. So, sin x is a common factor in both the left hand side and on the right hand side. So, we write it as sin x times 4 into 1 minus sin square x minus 2 sin x for this term minus 3 equals 0, which is same as writing sin x into 1 minus 2 sin x minus 4 sin square x equals 0. So, for this to be 0, either sin x should be 0 or this term in the square bracket should be 0, but sin x equal to 0 implies that the general solution for sin x equal to 0 is that x should be of the form n pi, where n is integer for all integer n. And let us now see how to solve the second equation, this particular term. So, either this is 0 or this is 0. So, for the second factor on the left hand side, we have 4 sin square x plus 2 sin x minus 1 equals 0, but this is a quadratic equation in sin x. So, the solutions are that sin x is equal to minus 2 plus minus square root of 4 plus 16 by 8. So, that is, so there are two solutions here. So, one is minus 1 minus root 5 over 4, and the other solution is root 5 minus 1 over 4. Now, we know that this is nothing but sine of 18 degrees. If you recollect, sine of 18 degrees was root 5 minus 1 over 4. So, this is sine of pi over 10 and we also know that sine of 54 degrees, which is 3 pi over 10, sine of 54 degrees is root 5 plus 1 over 4, and therefore, this is equal to exactly the negative of this, and therefore, here we can write sine of minus 3 pi by 10. So, from here, so for this equation to hold, we should either have sin x equal to sin pi by 10. So, this is of the form sin x equal to sin y, and therefore, the general solution here is n pi plus minus 1 to the power of n times pi by 10, n being integer, and then for the other equation sin x equal to sin of minus 3 pi by 10. This is also of the same form, sin x equal to sin y, and therefore, the general solution for this will also be n pi plus minus 1 to the power of n into minus 3 pi by 10 integer z. But if we go back to the original problem, so we had to find the solutions to this equation. So, and we derived it like this. So, it is the left hand side is a factor of these two factors. So, either sin x is 0 or this factor is 0. For sin x to be 0, this is the solution set, and for this other factor to be 0, we saw that either it should, so we saw that the other solution set is nothing but the union of these two sets, and therefore, the final answer is this set union n pi plus minus 1 to the power of n pi over 10, n being integers, union n pi plus minus 1 to the power of n into minus 3 pi by 10, again n being integers. So, this is the general solution set to this trigonometric equation. In the next class, we will discuss some more solution to some more trigonometric equations. Till then, thank you.